Thanks. All right, let's get started. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for these students. I just pray that you'd just work great things in their lives this semester. Just pray you just glorify, you be glorified in what we do here this day, and just pray you bless this class, Lord. In your name I pray. Amen. Okay, so last Thursday, I showed you part of what I refer to as the unreasonable effectiveness of differentials. And what I showed you basically was that if you had a couple of equations and different variables related by given equations, long story short, you can take the differential of each equation and solve for the differentials of the dependent variables you're interested in, and then just read off partial derivatives from coefficients of the differentials of the independent variables. And it's really kind of amazing that you can just do that. And the reason that you can do that is something called the implicit function theorem, which is something I've never even stated, and yet by doing that calculation that you did with differentials, you're effectively implementing the implicit function theorem correctly. So this notation of differential, this differential notation it's subtle how much it encodes, and I don't think we really appreciate it too much sometimes. So I want to talk about differential equations today, and I'm going to talk about how we can talk about differential equations in terms of this differential notation. So in particular, remember this. We had dy dx is equal to some function of x and y. This is your standard first order differential equation. How do you solve these things? Well, if you had calculus 2 here, you should have seen some methods. For example, you should have seen maybe this example, dy dx equals minus y over x, right? How do you solve this? You separate and integrate. So, I'm sorry, I meant x over y. So that gives me y dy equals minus x dx. And then you integrate. 1/2 y squared is equal to minus 1/2 x squared plus some constant, right? But I'll rewrite this as x squared plus y squared equals to r squared, because that seems like a better way to present the constant. Of course, this differential equation has solutions which are circles, right? So this is an example of a separable differential equation, right? What other kinds of differential equations did you solve? Do you remember? Another example, maybe this one, dy dx plus y equals to, e to the x. This one is an example of a linear first-order differential equation. If you had calculus 2 here, we taught you how to solve this with the integrating factor method. So integrating factor method says, well, let's see here. My integrating factor, mu, exponential of the integral of the term next to the y. So here I've got, quote unquote, p equals to 1 in the usual notation, so I've got integral dx. So my integrating factor here is actually just e to the x. So the story goes, you take the differential equation you're given, you multiply by the integrating factor, and then you can solve it, right? So this is like e to the x, dy dx, plus y e to the x is equal to e to the x times e to the x, right? Which is what? E to the 2x. The beauty of the integrating factor method, of course, is that once you multiply by this integrating factor, what happens over here is what? Yeah, it's a product rule, right? This is d dx of e to the x times y. That's not an accident. It will always be the case once you multiply by the integrating factor that you're left with the integrating factor times the dependent variable. This is a necessary, this will happen. This is the method. It's inescapable if you calculated mu correctly. And then, of course, you can integrate. right? You can integrate both sides. What do you get? E to the xy is equal to 1/2 e to the 2x plus some constant. And then, so we find our solution. Y is equal to 1/2 sorry, 1/2 e to the x plus c e to the minus x. All right? Okay. I'm just reminding you the techniques maybe you've already... Now, if you haven't seen these before, it doesn't matter. You should still be able to do the homework without these, okay? I'm just using these as... I'm going to use these as examples to showcase the method of what I'm showing you today, all right? So here's the idea. We can trade... So I'm going to transition here and show you the new method. You can trade dy dx is equal to f for dy is equal to f dx, right? And I can do a little bit better than that. I can trade this for what? I can trade this for f dx minus dy is equal to 0. You're like, well, so what? Right? So what? Well, if I can find another function, let's call it g, right? If I can find another function, let's say g, such that the total differential of g is this so-called differential form, right? If I can find let's say big G such that what? The total differential of g is equal to f dx minus dy, then g of x comma y equals to a constant will be a solution of star. So let's try to play this game. Let's try to play this game with my examples. All right? First example. We had dy dx equals to, what was it? Minus x over y? Oh, not my Uber example, my example. Not the archetype, the one with the formula. Oh, I almost breathed coffee, which seems like it might be a good thing, but in fact it's not. It's one of the many wrong things to do with coffee. Yeah, I don't advise it. So if we change this to differential form, what we've got is y dy equals to minus x dx. But okay, we take a different perspective. This is x dx plus y dy. My question is, this is the differential of what function? Go away. It's my brother. Bye, Bill. Nope, end call. I probably called him in class earlier today. I've got it coming. Let's see here. He's also a math teacher. So what goes here? What's G? Yeah.
Well, if it was x squared plus y squared, it would be 2x plus 2y.
Mm-hmm.
Be over 2.
Exactly. So my claim is that x squared plus y squared divided by 2 equals to a constant solves dy dx equals to minus x over y. And I think you can see from your previous methods, I am being honest with you. If this is possible, all right, if it's possible to write your differential equation in what's called Pfaffian form, and if it's also possible that that Pfaffian form is obtained by the differential of a function, then the differential equation is said to be an exact equation. This equation was an exact equation. Let me put that in words. Let me write it down. You had a question? Yeah.
Can you explain one more time where you got the x squared plus y squared over 2 from?
He told me.
Oh,
Guessing. But, well, we'll get into that. That is, of course, a question, right? We just guessed. You guessed, right? Okay. Definition, if m dx plus n dy equals to 0, represents a differential equation. So what differential equation does it represent, by the way? Dy dx equals to what? Minus m over n, okay. Now, technically speaking, they're not entirely equivalent, right? I would argue this one, n equals to 0, es no bueno. Whereas over here, n equals to 0, well, yeah, whatever. N could be 0, no big deal. So I do think that this allows for sort of a larger domain of consideration if you start thinking about it. There are points in this which might not be included in that. The advantage of, so this what I just wrote here is known as the Pfaffian form of a differential equation. Pfaffian form. That's what it's called. Pfaff was some 19th century mathematician who did early work in this stuff. And so if the Pfaffian form of the differential equation, let me call this thing omega. Let's call it omega, all right? This whole thing omega. If omega is equal to the differential of g, then omega equals to 0, aka dy dx equals to minus m over n, is an exact equation, which is huge because once you know that omega is equal to dg, the solution to the exact equation, those solutions are simply level curves of g. Theorem m dx plus n dy equals to 0 exact implies, and if this is dg, g of xy equals to a constant, those are your solutions. Now, but your question remains, how do I find the big G? How to find G? It may be instructive to try this method out on this other example, right? See what happens. So we got what? We've got I'll start with dy dx is equal to e to the x minus y. Multiply by dx, I get dy is e to the x minus y dx, right? And so what do I get? I get e to the x minus y dx minus dy is equal to 0. There I wrote it in the Pfaffian form. Okay. Now, I want to point out to you something if we have, so I don't know if I, sidebar, all right. Well, I guess no, indecision is my chief nemesis. So suppose that this is equal to dg. What would that mean? That would be the solution. You're getting ahead of the story, yeah. Yes, but what is actually dg here? It's partial g, partial x dx, right? Plus partial g, partial y dy. So to find the g, I have to make these things match up, right? So I have to solve two related equations. I have to solve partial g, partial x is equal to e to the x minus y, and I have to solve partial g, partial y is equal to minus 1. There's actually no guarantee that I can solve these equations. There's a reason we call the other example an exact equation. It's an equation of a particular type. Like, not all equations are exact. I think we're going to find out that this one isn't. We'll find out soon. So how would you, you try to solve this, right? So if I integrate this with respect to x, what do I get? E to the x, right, minus xy plus some constant, which is depending just on what? Y, right? Then what we should do, to be careful, is we should take this, all right, and plug it in down here and see what happens. So what does this give us? Partial g, partial y is equal to, what's the derivative of this with respect to y? Negative x plus dc1 dy. I say total derivative because this is only a function of y, so the partial derivative becomes an ordinary derivative. And what's that equal to? Allegedly minus 1, right? But this is an absurdity. Why? Why is that preposterous? What does that equation say? It says x, and there's a function of x plus a function of y is equal to minus 1. How can the x cancel? Unless there's an x dependence on dc1 dy. But c1 is just a function of y by assumption. It's just not possible to have such an equation. So what does that mean? It's not an exact equation. Let me trace the source of what was the impossible thing to state? The impossible thing to state was that differential equation has the form dg. There is no g. All right? So this means, I'm going to call this one star. So star is not exact. So this is very much related to the question that we've been looking at, finding a vector. We have a function, we have a vector field, and then we ask the question, can you find it as the gradient of a function? Some vector fields can be written as the gradient of a function, some can't. This is very much related to that question. So can you see some kind of test we could do generically speaking? Let me show you. So here's what we do. If m dx plus n dy is equal to dg, right? That means it's partial g, partial x dx plus partial g, partial y dy. Then what's that say? That says that m is partial g, partial x, and n is partial g, partial y. That means that m and n are connected. They're connected by the function g. What do we know about partial derivatives for g? Partial squared g, partial x, partial y, is equal to partial squared g, partial y, partial x, assuming that g is a nice enough function, and we will make that assumption. It has to be twice continuously differentiable to apply this theorem, Clairaut's theorem. What does that say in terms of m and n? See, this is partial x of partial g, partial y. What's partial g, partial y? Partial g, partial y is n. Partial x, partial y of partial y of partial g, partial x. Partial g, partial x was m. So we have a simple no-go theorem. A no-go theorem. If omega, let's say if omega equals to m dx plus n dy equals to 0, has partial m partial y not equal to partial n partial x, then omega is not exact. It turns out that the converse is true, provided we know that the exactness condition is met over a simply connected domain. But to reverse this, to suppose that partial m partial y is equal to partial n partial x, that equation holding true, I need to have that's true in a simply connected region in order to reverse this logically. We'll talk about that later in the course when we have the appropriate tools to work it out, Green's theorem. But this is a simple test, so you can see that this fails that test, right? Because what's this have? Partial m partial y is what? M here is that, right? And so that's minus 1. What's partial n partial x? It's not exact. So at this point you might be like, well, if all equations aren't exact, then why bother with this method, right? Well, some equations are exact to start with. There's one reason to do it. But this Pfaff, he was pretty bright. He proved a theorem which says that if you have a differential equation in, Pfaffian form, there exists some function that you can multiply the equation by and make it become an exact equation. This is always possible. So, do you care to guess what function we might want to multiply here to make that become an exact equation? What? You're back here? Oh, man. I should leave the room for 3 minutes. Let you guys catch up. I'll be back. No.
I was going to ask if there was any other way other than that no-go theorem to tell if just from those equations it wasn't exact.
The no-go theorem is the simplest test I know of to check exactness. But there is another method, I just showcased it, which is just try to find g and let it blow up in your face. Right, that's what we did. We just assumed it was exact, tried to work out the partial g partial x equal to the x coefficient, partial g partial y equal to the y coefficient, and we saw how we failed miserably.
But I didn't quite see how exactly we failed.
Because this equation is nonsense. I have a function of x plus a function of y is equal to a constant. That's impossible. That means that the only way this could cancel out and give you minus 1 is if this had a genuine x dependence. If I take the partial derivative of this equation with respect to x, what do I get? Exactly. Contradiction. Sorry. I should have got to something. I should have made my contradiction get to something crazier. But, I mean, for me, there's the proof that when you have something of x plus something of y, it's nonsense. If you partial differentiate with respect to either x or y, you'll get the point of the nonsense, yeah. Well, x is the key here. But.
So what you're saying is there's a function by the...
Can I erase now? I'm sorry.
There's a function where you multiply star by that would make...
If I'm about to do that again, you should just go like, no! Like that before I do it, and I'll stop. I'll drop it. I'll drop the eraser. It's like that. Just like the appropriate like cry of mercy. Yeah, yes?
Okay. So you're saying there's a function that we multiply star by to make the new star exact?
Yes. Anyone care to guess what we should multiply by? Oh, question, yeah.
All right. So do you not know that it's not exact until you try working through it and doing the partial derivative of each of the coefficients?
No, I know. I can test because of the no-go theorem. If partial m partial y is not equal to partial n partial x, it's not exact. This is a necessary consequence of both of the coefficients of dx and dy appearing from partial derivatives of the same function g. This essentially is the condition that the partial derivatives commute for the solution function. So, like I said, just from looking at this, these not equal by the no-go theorem and the thing I just erased. What I just erased was the proof of the no-go theorem. Okay, so again, would you guys want to multiply by to make it exact? Any guess? Y minus x? No. I don't think that's what you want. 0. 0 equals to 0. I think that includes, what's the solution to 0 equals 0? There are a lot of solutions to that. I'm going to put you guys out of your misery. How about we multiply by, I don't know, it worked for us before. Maybe this. Why don't we multiply by e to the x? Okay. So what happens? Multiply by e to the x, we get e to the 2x minus y e to the x dx minus e to the x dy is equal to 0. So this is my new m. Let me call it m bar and call this one n bar. So what's partial m bar, partial y is what? Minus e to the x. Partial n, partial x, minus e to the x, voila. Exact. That doesn't solve it. It just tells me that I can solve it using the method of exact equations. And that method is, again, to find what this is the differential of. dg equals this for what g? So what's my g? Shall I solve it the careful way or the guessing way? I will solve it the boring, careful way. I shall not erase these things as to not offend. So what do I need to solve? I need to solve partial g, partial x, e to the 2x minus y e to the x, and partial g, partial y equals to, minus e to the x. I don't know. What do you guys want me to start with? Doesn't matter. Want to integrate the first one and the second one? Your choice. First one? All right. So 1 implies that g is equal to 1/2 e to the 2x minus y e to the x plus some constant, say c1 of y, integrating with respect to x, holding y fixed. Now what do I do? Plug that into 2. What's that give us? Differentiate this with respect to y, what do we get? Minus e to the x, right? Plus dc1 dy equals to what? So what I'm just doing is this partial derivative gives me these terms, all right? And then that has to be equal to minus e to the x, right? But you see, now that it's exact, we don't come to that nonsense equation. We have a balancing of the x kind of terms. They cancel out, and we're just left with dc1 dy equal to 0, which means you can take c1 to be a constant, and you're good to go. So what's our g? G of xy, something like 1/2 e to the 2x minus y e to the x. And the theorem, which I have been using but haven't really quite proved yet, the proof of it's just the chain rule, is that this equals to a constant is the solution to the given differential equation. So what's the solution then? 1/2 e to the 2x minus y e to the x equals to some constant. I let c1 be 0. So I mean, I can make that choice as long as I put a constant down here. I only need one constant for my solution set. Different choices of the constant give you different solutions to the original differential equation, right? There's always some sort of one family parameter of, there's always more than one solutions to a differential equation, right? Just like there's more than one integral for a given, for an integral, the antiderivatives differ by a constant. For these differential equations, the solutions differ by a constant too, but maybe not just as a vertical shift, right? They could be families of circles or other more interesting things like this. Although I think this one I can rewrite, right? Y is equal to 1/2 e to the 2x minus c e to the minus x. It's the same thing we got before. Just my c has become minus c, I think, but whatever. Just a constant. So this integrating factor method that we teach you in Calc 2 is really just the tip of the iceberg. Given non-exact differential equations, there's these things called integrating factors you can sometimes find and multiply by and make it exact. Don't get too excited, though. The problem of finding the integrating factor in general is more difficult than solving the differential equation. So this advice I'm giving you isn't terribly useful. I mean, how did I know e to the x was the thing we need to multiply by? Yeah, I just pulled it from the thin blue sky mostly. It's because I've done this before, but I mean, it's a much more difficult question to ask. How do you know what the integrating factor should be? There's a section in your book, actually not your book, but the edition 8 of your book. It would be like section 16.10 in your book, although there's stuff in chapter 16 we've yet to cover, right? We haven't talked about maximums, haven't talked about minimums, any of that stuff. That's in the next test, not this test coming up, right? This next test is coming up, it's just differentiation mostly, right? It's tangent spaces and normal vector fields and such, chain rule. But it would have been 16.10 probably. It used to be 15.9, and this is from the 8th edition, and I scanned it, I'll post it, and it's basically just on an exact differential equation, and there's a bunch of nice problems you can try at the end out on this. It's nice. Rather than doing more of this, I want to make a connection because, yeah, go ahead.
I just had a question
Mhm.
about partial derivative of e to the 2x. Why is that 1/2 e to the 2x and not 2? It's the integral. It's not the function. Oh, you're integrating it, not right.
That's because that's coming from this term, not that term. When I differentiate this with respect to y, it picks up this term, but the y is gone. Partial derivative with respect to y picks up this term. This term's 0 because it's constant with respect to y.
But in that first step, you got the 1/2
Oh, where's-
2x because you.
Oh, yes. Very true, yes.
And then how did you get from that to the next step?
I differentiate with respect to, I'm plugging into 2.
Yeah.
Partial. So I differentiate this with respect to y. That's 0 because there's no y dependence. This becomes minus e to the x because it's just the y differentiates to 1. And that becomes dc1 dy. Okay. Now, let's talk about the connection to vector fields. Right? Let's talk about the connection to vector fields. Make sure I have. And I'll show you how to actually visualize some of these things. So we have omega is something like m dx plus n dy, right? And we've been studying that equal to 0, right? I've been claiming that the level curves of this have to, if that's equal to dg, right? If this is equal to dg, then that equals to 0 has g of xy equal to a constant as solution. Now, how would you actually, let me try to give you some evidence of how to flesh that out. So let's see, let's let gamma, or how about r of t? And so, and let's let r of t be x of t, comma y of t, all right? So let's take the parametric viewpoint. Suppose you have a parameterization of the level curve. What's that mean? Right. Yeah, g of r of t is equal to c, right? Or, and so if you take the derivative of this with respect to time, what do you get? So let me write it out, x of t, y of t. We use the what? The chain rule, right? So it's the gradient of g at r of t dot dr dt. Let me write that out in more detail, though. That really is partial g partial x, comma, partial g partial y, dotted with dx dt, comma, dy dt, right? Which is what? I mean, partial g partial x dx dt plus partial g partial y dy dt. I mean, I could have written that at the start of all this and not written those other two steps, but I'm just trying to remind you. Chain rule for a level function composed with a path. Now this is equal to 0, right? But hey, in this particular context, if I'm assuming that this isn't just any g, it's g connected to a particular Pfaffian form, a particular differential equation. So what is the significance? Partial g partial x is what? M. This is n. So what do we have? We have m dx dt plus n dy dt is equal to 0. Mm-hmm.
Could you arrive at the same result by dividing omega by dt?
I could, but that would be what I would call formal nonsense, which I'm all for. I'm all for, because I'm about to tell you some formal nonsense, which is that this tells you that m dx plus n dy is equal to 0. I can be more precise, though. I just worked it out for a parameterization of the level curve, right? What if you take the parameter to be x? What if you take x equals to t? In my derivation, what does that give you? So you have g of x comma, say, y of x equals to a constant, right? Same derivation I just did. What does it give you? M dx dx, right? Plus n dy dx equal to 0. In other words, dy dx equals to minus m over n, which of course is what we want. So there you go. There's the proof. It's the chain rule. If you can write the differential equation in Pfaffian form, is the total differential of some function g, then g equals to a constant. Those level curves are solutions to the differential equation in question. Simple as that. Yeah? Question? No? No? But you see, what I just derived was something much more interesting. We just derived that if you have a parameterization of the level curve, then it also obeys this very much related differential equation involving dx dt and dy dt, right? Which is kind of neat. Let's see here. So my question then, so now that I got that proof out of our system. By the way, well, I'll shut up with that. Oh, where are you?
I'm good.
You're good? Okay. I've become paranoid now. My advisor, anytime somebody would tell him that they were good, he would always say back to them like, "Are you sure?" I don't know. It's kind of funny. But all right, so my question then is, what's the geometry here? You see, you could think about this being connected to a vector field, Mn, right? Right? There's some vector field you could think about f equals to Mn, right? And then you could think about the solution. If that's a solution, what's the relation between the solution geometrically and the function, the vector field Mn? Well, look at it. I mean, it's essentially what I just erased, and let's do that formal nonsense. M dx dt plus n dy dt equals to 0. Well, what is that? That is Mn dotted with dx dt dy dt is equal to 0. In other words, the solutions to the differential equation m dx plus n dy, they have to be perpendicular to the vector field m comma n. You're like, well, I hear what you're saying, but can you give me an example? Sure. How about this? X dx plus y dy. This was a good example. We've looked at this already. We know it's exact, right? So the vector field that's kind of corresponding, I mean, I might call it omega vector, right? It's like omega as a vector is what? xy, right? So I'm saying the solutions are perpendicular to that vector field wherever they meet. So what does the vector field x comma y look like? We've looked at this before, right? It's this guy. I mean, here's some These are integral curves to the vector field f, okay? What's an integral curve to a vector field? It's a curve whose tangents line up with the vector field, right? So if you look at this vector field, these are the integral curves of f.
So they're all pointing away from the origin.
Exactly. And I guess I said of omega. What curves, so I'm telling you the solutions to this differential equation are so-called orthogonal trajectories to those integral curves. That's what we found. Circles upon circles upon circles. See it? These are the solutions. Yep.
On this left-hand board, I guess over there too, would it be fair to say that that f is the gradient of r, or am I missing something?
Indeed, Luke has also perceived that there's something else we could say, comment, and that's a good comment to make. Omega equals to, m dx plus n dy is exact if and only if m comma n is equal to the gradient of g for some g. Indeed. In other words, it's an exact differential equation only if it corresponds to a conservative vector field. A vector field which can be written as the gradient of a scalar function is called a conservative vector field. So yes, there's this natural correspondence between exact equations and conservative vector fields. I'm very glad you asked that question. I would be, at about 10 minutes after class, I would have been like, oh man, I wanted to say that. So I'm very, very grateful for that question. Let me twist your head a little bit. So you want to use this. So we like to find integral curves to vector fields. It's kind of cool because it's hard to picture vector fields. It's much easier to picture integral curves to vector fields because you can kind of see where the vector field is, and then you know that the vector field like points along that line. So let's try this out. Suppose our vector field is given to be, I don't know, y squared x. Find integral curves to f. So now, here's what won't work. Let me just start out with what won't work, and you tell me why it won't work. I could try to go, well, I'm going to do y squared dx plus x dy. I'm going to try to solve that differential equation. The solution to that, that's going to give me my integral curves, but you see that won't give you the integral curves. Why? Solutions to that differential equation are what? They're orthogonal trajectories to the integral curves that we want. How can you take what I've written in green and twist it to get something that takes the curves to get the curves you want? Yeah? Switch them around, right? Almost. And one of them, flip one or the other sign. So now the solution to this, right, will be orthogonal, perpendicular, if you like, to the vector field, what, x comma minus y squared, the defining vector field for this differential equation. But if it's perpendicular to that, Someone did some bad algebra on the other side of that wall. So, this is Brano's dropping the logical hammer upon them. Let's see here. But if it's perpendicular to that, right, that implies that it's parallel to this. Because in 2 dimensions, if it's perpendicular to the perpendicular, you're back where you started again. Because perpendicularity is essentially rotation by 90 degrees. Right? So if you rotate by twice, you're back where you started, or anti-parallel to what you started, yeah.
Is that like doing the negative reciprocal of the slope?
Yeah, I think that's fair. If you take the negative reciprocal of the negative reciprocal, you're back where you started again. Great, great. Now, the thing is, this I can solve pretty easy, right? I think. What's the solution to that? Well, this is the differential of 1/2 x squared minus 1/3 y cubed equal to 0. So you see what I'm looking for, then the answer 1/2 x squared minus 1/3 y cubed equal to a constant. The solutions to this level equation, solutions to that equation are the integral curves to that vector field up there. This was you asked me about what's the geometry of, or you asked me a question about like the geometry of gradients or something. This was what I was thinking about. This whole discussion is the answer to that question I was mentioning. Although I still don't know if I've quite got back to your question. I don't remember what your question was. It's okay. It's all right. I'll survive. Y gradient is a normal. Oh, that I've answered. I mean, yeah. Oh, yeah, that we answered the other day. But I do think this gives you more insight as to the geometry of the gradient in a kind of. I mean, it's way easier to solve these kinds of equations. I don't know if you guys. Well, you probably haven't seen it, but this is what's known as an autonomous. I can't spell it. System of ODEs, something like this. You could have dx dt equals to x plus y, dy dt is equal to x minus y, say. Do you guys know how to solve these kinds of things? Probably not, right? I mean, I hope not. If you already know this, then why are you bothering to take differential equations? Because apparently you already know how to do the stuff in there. Good. But if you believe in this silly method of differentials, right, maybe you believe that you can cancel dt somehow. Right? Like, this would be what? I could eliminate dt, right? What if I do this, like dy? Certainly dy over dx, it ought to be the same as dy dt over dx dt, right? And that should be what? X minus y over x plus y. See, we eliminated time at the level of calculus. And now I have something like x plus y times dy is equal to x minus y times dx. And maybe I can solve this by the stuff we've been doing, right? So this is what? Oh, that's weird. Oh, I guess it's okay. I don't know. What do you think? X. So I got what? I got y minus x. Actually, I'm not altogether hopeful about this one. Y minus x dx plus x plus y plus x dy equals to 0. If this is m, and if this is n, is this exact? I don't know. Partial m partial y is what? 1. Partial n partial x? 1. Oh, okay. So it's exact. Can you guys tell me what this is? So we need to solve partial g partial x equals to y minus x, and partial g partial y equals to y plus x. Can we do that? G is equal to xy minus 1/2 x squared, and this tells me g is equal to 1/2. Oh, that doesn't seem right. I mean, plus. I think I'm getting a 1/2 y squared here. I don't know. I'm not too happy about that. I know, I'm just using the integrate both and then compare method. It doesn't always work. So what's the answer? You know, yeah. What? Y is what? Oh, so you want me to do partial g partial y, which is what? X plus dc1 dy equals to what? Y plus x, right? Oh, I see. So apparently dc1 dy is equal to y. c1 is equal to 1/2 y squared plus a constant possibly. So I get g of xy is xy minus 1/2 x squared plus 1/2 y squared. And so that equal to a constant. There you go. That's, well, is that the solution to this? Not quite, right? I need functions of time. I have an equation. So the parameterizations of the thing I boxed at the far right there, those would be the actual solutions to the given autonomous system of ODEs. I wanted to show you this as another example of this unreasonable effectiveness of differentials. Like just this idea you can cancel out dt's and solve the equation. It really does work that way. I'm going to show you a picture, if you don't mind. Come on. Come on. Come on. We're all waiting here. You can do it. What a monster. He made that girl run down that strip with a broken ankle, as if the sporting event is worth a lifetime of pain in your ankle. I tell you. You guys know what I'm talking about, are you? There's this Olympics, this girl, she broke her ankle, and then like the coach is like, you can do it. You can do it. And then she like did it again, and then like completely mangled her ankle on the second. One of these, you run and then jump and then spin over the air and I don't know. Come on! Oh, I know what it is. We could be here all day long. It wouldn't help. Come on. Come on. Come on. All right. So this